Okay, so this video is going to focus on the stoichiometric relationships in IB Chemistry Topic 1. Beginning with Topic 1.1, the particular nature of matter. Alright, firstly we're going to look at the particular nature of matter. So the essential idea behind this is that physical and chemical properties depend on the way in which different atoms combine. So the relationship between the amount of reactants and the amount of products in a chemical reaction is a stoichiometry of the reaction. The application of ideas of stoichiometry allow chemists to determine what amounts of substances should react together and to predict how much product should be formed. So the particle theory of matter states that particles occupy a volume in space, have mass, and are in constant motion. Now, beginning with states of matter, so first off, matter is everywhere, everything is made up of matter. So matter can exist in different states depending on the temperature and pressure of the environment. The different physical states are characterized by the different arrangement and movement of the particles. So these consist of, concerning the IB chemistry course, is solid, liquid, and gas. It's noteworthy that a fourth state of matter, plasma, also exists, however it is not covered in this curriculum. So the state of matter is dependent on the possessed kinetic energy, and kinetic energy is the energy related to the motion of an object. Alright, so this here outlines the three states of matter that we're going to look at. So we have solid, liquid, and gases. For solids, the particles are closely packed. They have strong forces between the particles. The particles vibrate in a fixed position, and the solid has a fixed shape and a fixed volume. For liquids, the particles are slightly more spread out than solids. They have weaker forces between particles. The particles can vibrate, rotate, and translate, which means they move around each other. And there is no fixed shape, and the liquid takes the shape of the container that it is contained in, but it has a fixed volume. Gases, the particles are very spread out normally, unless under very high pressure. There are negligible forces between the particles. The particles vibrate, rotate, and translate much faster than in a liquid, and they can also move further from each other. They don't have to be in contact. There is no fixed shape, so the liquid will expand to occupy the available space. The gas will expand to occupy the available space, and there is no fixed volume. Okay, so continuing with changes of state. Changes in state at a constant pressure are directly related to a change in temperature. Therefore, as we increase the temperature, we're going to change state from solid to liquid to gas. So an increase in temperature causes an increase in the average kinetic energy of the particles within the substance. And when heated, particles gain kinetic energy, and they use this kinetic energy to be able to overcome the intermolecular forces that exist between them, resulting in a change of state. This diagram here outlines the changes of state. So going from left to right, so evaporation is from a liquid to a gas, and this requires the absorption of energy. Whereas the reverse of this is condensation, from a gas to a liquid, and this releases energy. From a liquid to a solid is freezing, and this releases energy. From a solid to a liquid is melting, and this absorbs energy. From a gas to a solid, this is known as deposition, and this is releasing energy. And a solid to a gas is sublimation, and this absorbs energy. Okay, so it's important to make a distinction between boiling versus evaporation. So evaporation and boiling both result in a change from a liquid to a gas. However, evaporation only takes place at the surface of the liquid and can occur at temperatures below the boiling point of the liquid. Boiling occurs at specific temperatures and takes place throughout the liquid. So evaporation has bubbles only at the top of the liquid, whereas boiling has bubbles throughout the liquid. Another important point to make is the changes of state can be represented in equation form as follows. So for instance, for melting, you have the brackets S for the solid, and then the brackets L for a liquid, and it's represented here in sublimation and condensation as well. The essential idea is that the S stands for solid, the L stands for liquid, and the G stands for gas. Okay, so now we're going to look at heating and cooling curves. So on the right, there is an example of a heating curve. So over time, the temperature is increasing. So in the upward sloping regions, so that is at the start of the solid, at the start of the liquid, and the start of the gas, the temperature increases as the substance is heated. The kinetic energy of the particles increase during this time, and they vibrate and move faster, therefore their temperature is increasing. However, it's notable that during the changes of state, so from solid to liquid and liquid to gas, this is the melting point and boiling point respectively, the temperatures remain the same. So the reason for this is that at these points, the energy is being used to overcome the intermolecular forces that exist between the particles. So during melting, the energy input is being used to overcome the intermolecular forces that hold the particles in the solid fixed positions, while during boiling, the energy input is being used to overcome the intermolecular forces that hold the particles in the liquid together. So once the change of state is completed, that is, all the bonds, all the intermolecular forces are broken, the temperature will then start to increase once again. It is noteworthy that melting and boiling are both endothermic processes, that is, that they gain energy from the surroundings, whereas if this was a cooling curve, the opposite of these two would be exothermic properties, and they would release energy into the environment. Looking at density, this is very short. It's just density of a substance's mass per unit volume. Therefore, density equals mass divided by volume, or mass equals density times volume. And this can be used to solve questions involving volume, density, and mass. Okay, now elements. So an element is made up of only one type of atom, and it cannot be broken down by chemical means into a simpler substance. An atom of an element is the smallest particle that shows the characteristic properties of that element. Now, compounds. Elements combine in chemical reactions in a fixed ratio to make compounds. A compound is a substance that is composed of two or more different atoms that are chemically combined. When atoms of different elements react, they lose their characteristic properties, and the properties are replaced by those of the new compound formed. So for instance, in that of sodium chloride, sodium is a very reactive metal, chlorine is a toxic substance, but together they form table salt, which we use every day and is non-toxic. And now the distinction between molecules versus compounds. So a molecule is a group of two or more atoms held together by chemical bonds. A compound, however, is a substance which is formed by two or more different types of elements which are chemically united in a fixed proportion. All molecules are not compounds, all compounds are molecules. Now we will explore mixtures. So we have homogeneous mixtures and heterogeneous mixtures. So a mixture is composed of two or more substances that are not chemically combined, meaning that each substance retains its original properties. A homogeneous mixture has the same composition throughout, whereas a heterogeneous mixture has a non-uniform composition. So this shows here some examples of a homogeneous versus a heterogeneous mixture. So for instance, air, steel, wine, and rain are all examples of homogeneous mixtures, as they have a uniform distribution of the particles. Whereas a heterogeneous mixture, examples include ice water, cereal and milk, oil and vinegar, soil, because they have a non-uniform distribution of particles. So looking a little bit further into homogeneous mixtures are not chemically combined, but they do not separate physically on standing. Each different component will have its own boiling point, which means that components can be separated by fractional distillation. Fractional distillation is a technique used to separate the components of a mixture based on their different boiling points. So solutions are also examples of a homogeneous mixture. They're composed of solutes dissolved in solvents. And two liquids that form a homogeneous mixture are said to be miscible. Moving on to heterogeneous mixtures. So heterogeneous mixtures will separate into two separate layers on standing. For example, water and oil. The two phases in the mixture of water and oil are clearly visible, and therefore they are said to be immiscible. Okay, so looking at chemical reactions involve the formation of new chemical substances. In a chemical reaction, the atoms present in the reactants are rearranged and joined together to form products. The chemical change taking place during a reaction can be represented by a chemical equation. In the chemical equation, the reactants are on the left of the arrow and the products are on the right. According to the conservation of mass, in a balanced chemical equation, the number and type of each atom must be the same in the reactants and products. Atoms are not created or destroyed, they are only rearranged to form new products. Numbers in front of each formula in a balanced equation are called the stoichiometric coefficients. They tell us the molar ratios between the reactants and products in a balanced equation. A tip here is that if in the exam, in a multi-choice question, you're asked to give the sum of the coefficients, don't forget that there is the coefficient of 1 in front of, in this equation, for example, the oxygen. So state symbols. So chemical equations show the physical state of the reactants and products through the use of state symbols. So here we've got solid represented by S, liquid by L, gas by G, and if it's an aqueous solution, AQ. Looking at diatomic molecules, so there are 7 elements that exist as diatomic molecules under standard conditions. These include hydrogen, oxygen, and nitrogen, and the group 17 elements including fluorine, chlorine, bromine, and iodine. So iodine, so anions are negatively charged and cations are positively charged ions. This table of ions here is necessary to memorize for the IB exams. So the ammonium ion is NH4+, carbonate ion CO32-, hydrogen carbonate ion is HCO3-, hydroxide ion OH-, nitrate ion NO3-, nitrate 3 ion NO2-, phosphate 4 ion PO4 3-, phosphonate ion PO3 3-, sulfate ion SO4 2-, sulfite ion SO3 2-, ethanodioate ion C2O4 2-, peroxide ion O2 2-, and the name of the acids and their formula: hydrochloric acid HCl, nitric acid HNO3, phosphoric acid H3PO4, sulfuric acid H2SO4, and ethanoic acid CH3COOH. So now looking at some types of reactions. So we have combinational synthesis reactions involve the combination of 2 or more substances to produce a single product. Decomposition reactions involve a single reactant being broken down into 2 or more products. Single replacement occurs when one element replaces another in a compound. And double replacement occurs between ions in solution to form insoluble substances and weak or non-electrolytes. Looking at atom economy, so atom economy equals the molecular mass of atoms of useful products divided by the molecular mass of atoms in the reactants. Now on to topic 1.2, the mole concept. Okay, so in terms of the mole concept, the essential idea is that the mole makes it possible to correlate the number of particles with the mass that can be measured. Looking at relative atomic mass, so the masses of atoms can be compared using a relative scale. On the scale, an atom of carbon-12 is assigned a relative mass of exactly 12, and the relative masses of other atoms are compared to this reference point. So, as a definition, the relative atomic mass is the weighted average of an element's naturally occurring isotopes and their relative abundance compared to 1/12 the mass of the atom of carbon-12. Now, as this is a relative scale, the values for relative atomic mass are dimensionless. So the mass 1/12 of an atom of carbon-12 is known as an atomic mass unit, and the mass of one atomic mass unit is 1.66 times 10 to the power of negative 27 kilograms, and this is found in the data booklet. So the idea of relative atomic mass comes from the fact that in any natural sample of an element, it will be made up of a mixture of different isotopes, and each isotope will have a relative abundance. So isotopes of the same element are those that have the same number of protons but a different number of neutrons, and thus have different atomic masses. Extending this further, we'll look at the relative formula and molecular mass. So the relative formula mass and the relative molecular mass allow us to compare the relative masses of different compounds. So the relative mass or molecular mass of a compound is the weighted average mass of the compound compared to 1/12 the mass of carbon-12. So this is found by adding up the relative atomic masses of all the atoms in the compound, and it is also dimensionless. Just another concept, molar mass is defined as a mass of 1 mole of a substance, and its units are grams per mole. So there isn't really any noteworthy difference between relative formula mass and relative molecular mass. Okay, so exploring the mole further, the mole is a convenient unit used to count very small particles such as atoms, molecules, or ions. These are all considered as elementary entities. So the concept of the mole is comparable to other counting units such as having a dozen eggs, so the dozen representing 12. The mole is a SI unit for the amount of a substance. So the amount of a substance is a measure of the number of specified elementary entities in a sample, and as said earlier, these can refer to atoms, molecules, ions, electrons, protons, neutrons, any other particle. So the mole is defined in two ways. So the first way is defined as containing exactly 6.02214.076 times 10 to the power of 23 elementary entities. However, it's also defined as the amount of a substance that contains the same number of particles as there are in exactly 12 grams of the isotope carbon-12. Avogadro's constant. The value for IB is 6.02 times 10 to the power of 23. So a mole of any substance contains the same number of particles. So whether that is calcium or potassium or carbon, 1 mole of those atoms will contain 6.02 times 10 to the power of 23 particles, or 23 atoms in 1 mole of that element. Although moles of different substances will have different masses. So in terms of mole calculations, so molar mass is equal to relative molecular mass. So the molar mass on the bottom there is just the relative molecular mass or relative atomic mass. And so moles equals mass divided by molar mass. And the mass is in grams, and the molar mass is in grams per mole. It is important to keep these units the same. And just leading on from this, if you are asked to find the mass of 1 molecule of a substance, for example, 1 molecule of methane, you simply find the molecular mass by adding and finding the relative molecular mass, and then dividing this by Avogadro constant. So moving on to empirical and molecular formula. So the empirical formula is the simplest whole number ratio of atoms in a compound, whereas the molecular formula is the actual number of atoms in a compound. So percentage composition by mass. The percentage composition by mass expresses the mass of each element in a compound as a percentage. So to work out the percentage composition by mass, you divide the mass of the element in the compound divided by the molar mass of the entire compound and multiply that by 100. So for example, determining the percentage by mass of carbon and glucose. So there are 6 carbon atoms in the glucose molecule, each with a molar mass of 12.01 each, and the whole molecule together is 180.18 grams. Therefore, the percentage composition by mass of carbon and glucose is 39.99%. Calculating empirical formula, so that is calculated by using this percentage composition by mass of a given compound. So step 1 is we will find the percentage, find from the percentage composition by mass, you'll find the mass of each element in 100 grams of the compound. So step 2 is you find the amount of moles of each element present. And then we find the simplest whole number ratio, which is used to find the empirical formula. So also just a note that if a whole number ratio is not obtained, a multiplication factor must be applied for it to be a whole number ratio. So let's do an exemplar calculation. So the question states that the percentage composition by mass of aluminum chloride is 20.3% aluminum and 79.7% chlorine. So we are asked to determine the empirical formula of aluminum chloride. So first we'll find mass in 100 grams. So using 20.3%, that gives us 20.3 grams. Using 79.7%, that gives us 79.7 grams of aluminum and chloride, respectively. We find the moles of each of these. So we define the moles. We get the mass divided by the molar mass of aluminum, gives 0.752 moles. And the same for chlorine. The mass of 79.7 divided by 35.45 gives us 2.25 moles. To find the ratio, we will divide both of these moles by the smallest number of moles, so divide both of them by 0.752, which gives us a ratio of 1 to 3. Therefore, the empirical formula of aluminum chloride is AlCl3. Calculating molecular formula. So this is calculated using the molar mass of the empirical formula. And so we divide the molar mass of the molecular formula, which is normally given to us, by the molar mass of the empirical formula to find the multiplication factor of the empirical formula, which allows us to find the empirical formula. So continuing from the example of aluminum chloride, so we're given that the molar mass of aluminum chloride is actually 267 grams per mole. And so we need to find the relative molecular mass, or the molar mass of the empirical formula, which is calculated as 133. Therefore, we divide the molecular formula molar mass by the empirical formula molar mass to give us 2. Therefore, we need to multiply our empirical formula, by 2, giving us a molecular formula of Al2Cl6 instead of AlCl3. Okay, we're now going to look at the different methods of calculating empirical formula from experimental data. So the first method is heating using a crucible and measuring the change in mass. So the calculations will involve finding the moles from the mass, which will be given by a table, and you'll subtract it to find the mass of each compound, which you can then find the moles using the molar mass, and then ratios to empirical formula. So the possible sources of error for this method is that the original substance was not pure, the product was not what it was expected to be produced, and some product was lost when the lid of the crucible was removed to allow oxygen to enter for the reaction to occur. The next method is the water crystallization of a hydrated compound. So the water of crystallization is the number of water molecules that are present in one formula unit of a salt. So the water of crystallization can be determined experimentally by heating a hydrated salt until the water evaporates off. It's noteworthy that this process needs to be continued until the remaining salt is at a constant mass, which shows that all the water has been evaporated, and this just leaves the anhydrous salt. So using the mass before and after the evaporation allows for the calculation of the water of crystallization, which is then used to find the moles of the salt and the water, and then finding the ratio to then find the empirical formula. The assumptions made during this is that the mass is only due, or the mass change that's measured is only due to the loss of water. And the second assumption is that the crucible does not absorb water. And the third assumption is that anhydrous salt does not decompose. The final method is combustion analysis. So for this, we're going to do an example. So the example is that a 0.250 gram sample of a compound containing carbon, hydrogen, and oxygen undergoes complete combustion to produce 0.366 grams of CO2 and 0.15 grams of H2O. We're asked to determine the empirical formula of the compound. So the first step is that we need to determine the mass in grams of carbon and the 0.366 grams of carbon dioxide, and the mass in grams of hydrogen and 0.15 grams of H2O. So this is noteworthy that the oxygen comes from the atmosphere, so we're not looking at the oxygen in these compounds just yet. So to find the carbon, we'll multiply the amount in grams of carbon dioxide by the percentage composition mass of carbon in CO2, which gives us 0.0999 grams. We'll do the same for hydrogen, so we'll multiply the amount of water in grams by the percentage composition mass of hydrogen in the water, which gives us 0.0168 grams. The following step is then to determine the mass in grams of oxygen in the sample, and we do this by subtracting the mass of the carbon and hydrogen that we had found from the total mass of the sample. So we'll minus off 0.25 grams, or minus the grams we found of carbon and hydrogen, giving us 0.133 grams. Then we'll use this and each atom's or element's respective molar masses to find the moles, and then we'll find the simplest whole number ratio to then find the empirical formula. Moving on to topic 1.3, reacting masses and volumes. So reacting masses and volumes, the essential idea is that mole ratios and chemical equations can be used to calculate reacting ratios by mass and gas volume. First thing we're going to look at is limiting and excess reagents. So the coefficients in a balanced chemical equation tell us the molar ratio of the reactants and products. For example, take this equation here for magnesium plus oxygen giving magnesium oxide. The coefficients here tell us that 2 moles of magnesium react with 1 mole of oxygen to produce 2 moles of magnesium oxide, giving a molar ratio of 2 to 1 to 2. Molar ratios are used to determine limiting and excess reagents. The limiting reagent or reactant limits the amount of product that can be made in the chemical reaction, and the excess reagent is a reactant that remains at the end of the reaction. Okay, so now we're going to look at a worked example. So iron 3 oxide reacts with carbon to produce iron and carbon dioxide according to the following equation. So we have 2 iron oxide plus 3 carbons gives 4 iron and 3 carbon dioxide. So there's 500 grams of iron 3 oxide is reacted with 500 grams of carbon. Determine the limiting and excess reagents. So step 1 is to find the number of moles in each reactant. So the number of moles in the iron oxide is 500 divided by its molar mass of 157.7, giving 3.13 moles. The number of moles of carbon in 500 grams is 500 divided by its molar mass of 12.01, giving 41.6 moles. Now, in step 2, we need to find the limiting reagent by dividing the amount of moles by each coefficient. So the iron, we're going to divide the 3.13 moles by 2, and the carbon, we're going to divide the 41.6 by 3. This shows that the limiting reagent is iron oxide, as there's far less moles than there are of carbon, and therefore the carbon is in excess. Okay, so looking at theoretical yield. So theoretical yield is the maximum amount of product that can be produced, assuming that all the limiting reactant has reacted. The actual yield is the amount of product that is actually produced in a chemical reaction. And percentage yield is calculated by dividing the actual yield by the theoretical yield and multiplying this by 100. So the reason that we calculate percentage yield is because the actual yield, or the theoretical yield, does not occur most of the time, and rather the actual yield occurs, which is lower than that of the theoretical yield. And so this can occur due to the loss of products from reaction vessels, impurity of the reactants, changes in reaction conditions such as temperature and pressure, also reverse reactions consuming products in equilibrium systems, and the presence of side reactions due to the presence of impurities. Now moving on to explore further into gases, we'll look at Avogadro's law and the molar volume of a gas. So first off, we need to look at the kinetic molecular theory of gases. So this is 5 principles, and they are as follows. Number 1 is that particles are in constant random straight line motion. Number 2 is that there are negligible forces of attraction between the particles, that is the intermolecular forces. Number 3 is the collisions between or with the walls of the container are perfectly elastic. This means that no energy is lost. Number 4 is that the distance between the particles is much greater than the size of the particles themselves. Therefore, gas particles have a negligible volume. Number 5 is that kinetic energy of particles in a gas is directly proportional to the absolute temperature in Kelvin. Okay, so Avogadro's law states that equal volumes of gases at the same temperature and pressure contain equal number of particles. So just a point to make is that at standard temperature and pressure, also known as STP, the temperature and pressure are defined as 273 Kelvin or 0 degrees C and 1 atmosphere or 100 kilopascals respectively. So at STP, 1 mole of any gas will occupy 22.7 decimeters cubed. Now this photo here shows this, although it does have volume of 22.4, but for IB the value is 22.7. So essentially what this is showing is that 1 atmospheric pressure at STP conditions, no matter what gas it is, they will have equal volumes and equal number of particles. However, the mass of the gas inside will not be the same. For helium, the mass of the gas is 4, whereas nitrogen is 28, and methane is 16. Okay, now looking at reacting gas volume ratios. So Avogadro's law allows us to deduce the volume ratio of reacting gases from the stoichiometry of the reaction. So here we have the reaction of carbon monoxide with oxygen to produce carbon dioxide. We can see that the ratio of volume between the carbon monoxide and oxygen is 2 to 1, and then the ratio of the carbon monoxide to the carbon dioxide is a 1 to 1. Looking more, we can now have identified a new equation that the amount in moles equals the volume of the gas divided by the molar volume of the gas. Okay, so exploring the gas laws. So ideal gases are those that exhibit the 5 postulates of the kinetic molecular theory as well as obeying the gas laws. So the first law is Boyle's law, and this states that at constant temperature, the pressure and volume of a fixed mass of an ideal gas are inversely proportional. This means that as pressure doubles, volume halves. So pressure times volume gives a constant, so therefore that gives us the equation P1 times V1 equals P2 times V2. The second law is Charles's law, and this states that constant pressure, the volume of a fixed mass of an ideal gas, is directly proportional to its absolute temperature in Kelvin. This means that as temperature doubles, volume doubles. And this means that volume divided by temperature gives a constant, or V1 divided by T1 equals volume 2 divided by temperature 2. Moving on to the third law, so Gay-Lussac's law states that at a constant volume, the pressure of a fixed mass of an ideal gas is directly proportional to its absolute temperature in Kelvin. This means that as temperature doubles, pressure doubles. So pressure divided by temperature gives a constant value. Also, pressure 1 divided by temperature 1 will equal pressure 2 divided by temperature 2. So the combined gas law is that volume times pressure divided by temperature equals a constant, which means that volume 1 times pressure 1 divided by T1 equals volume 2 times pressure 2 divided by temperature 2. The ideal gas equation from this is PV equals nRT. This means pressure times volume equals moles times a constant known as R times the temperature. So the ideal gas equation, so in PV nRT we got P is the pressure in pascals, V is the volume in meters cubed, N is the amount in moles of gas, R is the universal gas constant, which is 8.31 kilojoules per mole, and T is the absolute temperature in Kelvin. So the units of this are very important. You need to have these exact units, otherwise you'll get an incorrect answer. So, for instance, if we are given the pressure in kilopascals, you must multiply that by 1,000 to get pascals. And if you were given the volume in decimeters cubed, you must multiply that by 1,000. And then similar calculations will have to happen if you're given it in centimeters cubed. So, real gases, a gas that obeys the ideal gas equation and the laws is said to be an ideal gas. However, in reality, all gases deviate from ideal behavior to some extent, and these are described as real gases. So at very high pressures, gas particles are close together, and therefore the actual volume of the particles themselves becomes significant. And at low temperatures, the particles move less rapidly, meaning there is a greater opportunity for intermolecular forces between particles to have an effect. So this means that gases that are most ideal are those with low molar masses and weak intermolecular forces, and those that deviate the most from ideal gases are ones with high molar masses and strong intermolecular forces. So just a quick note is that under STP, the product of PV divided by RT is always equal to 1, and non-ideal gases will not equal to 1. So solutions and concentrations. So solutions, which are homogeneous mixtures, occur when a solute dissolves in a solvent. A dilute solution is one that contains a relatively small amount of dissolved solute, and a concentrated solution contains a relatively large amount of dissolved solute. The molar concentration of a solution is the amount in moles of a substance dissolved in 1 decimeter cubed of solvent. So we get concentration equals moles divided by volume, and this is given in decimeters cubed, and the unit is moles per decimeter cubed. However, concentration can also be expressed as in grams per decimeter, so instead of moles, that will be swapped out by grams, and it can also be expressed in parts per million. So concentration in parts per million will be the mass of the solute divided by the mass of the entire solution times 10 to the power of 6. So serial dilution. A serial dilution involves diluting a stock solution multiple times, usually by the same factor, which results in an exponential decrease in concentration. For example, if 10 centimeters cubed of 1 mole per dm cubed solution is made up to 100 centimeters cubed with 90 centimeters cubed of distilled water, the concentration will decrease to 0.1 moles per dm cubed. Furthermore, if 10 centimeters cubed of that second solution is made up to 100 centimeters cubed, once again with 90 centimeters cubed distilled water, the concentration will decrease to 0.0100 moles per decimeter cubed. Continuous dilutions will decrease the concentration by a factor of 10 each time. So looking at standard solutions, so a standard solution is a solution with an accurately known concentration. So primary standard solution is made up using primary standard, and primary standards have high purity, roughly 99.9%, high molar mass, as this reduces percentage errors in calculations. They have low reactivity, and it does not change composition in contact with air. That is, they are hygroscopic. So looking at volumetric analysis involves a precise measurement of volumes to calculate the concentration of a solution. The practical steps in the titration are as follows. So a titration is a method of volumetric analysis in which the concentration of a solution can be determined. In a titration, a burette is filled with a standard solution of known concentration, and this is known as the titrant. A carefully measured volume of the solution with the unknown concentration, known as the analyte, is placed in a conical flask below the burette. An indicator is used to determine the endpoint of the titration. So when doing a titration, it is necessary to undertake repeat trials. So the first trial is known as the rough titration, is not used to calculate the average volume. However, some subsequent trials with their subsequent volumes should ideally be within 0.1 centimeters cubed of each other. It's ideal to get 3 concordant values. These volumes are then used to calculate the average volume of the titrant used in the titration. So we're now going to look at a worked example. So a student carried out a titration to determine the concentration of a sodium hydroxide solution. So they used 25 centimeters cubed of the solution was added to a conical flask together with a suitable indicator. Hydrochloric acid was then added to the flask from a burette until the end point of the titration signaled by the indicator's color change. The average volume of 1 mole per decimeter cubed HCl added to the sodium hydroxide solution was 12.5 centimeters cubed. We are asked to determine the concentration of the sodium hydroxide solution, and we have been given the equation. So the first step is to calculate the moles of the titrant added to NaOH. So we need to use concentration equals moles divided by volume. And we know that the concentration is 1 and that the volume was 12.5 centimeters cubed. So that gives us a moles of 0.0125 of HCl. The next step is then to determine the molar ratio of HCl to NaOH from the balanced equation, and therefore the amount in moles of NaOH that reacts with the HCl. And as there is a 1-to-1 ratio between sodium hydroxide and hydrochloric acid, there is 0.0125 moles of NaOH. So the step 3 is then to calculate the concentration of this analyte, which is sodium hydroxide. So once again, we use concentration equals moles divided by volume. We now have the number of moles, and we have the volume of 25 centimeters cubed, which gives us a concentration of 0.5 moles per dm cubed. Another titration technique is that of a back titration. So a back titration is a technique which is useful for analyzing impure substances. In a back titration, an excess of titrant is added to the analyte, and the excess titrant is then titrated to determine how much excess titrant remains. Back titrations are commonly used when one of the reactants is insoluble in water but does not react with acid. So looking at a worked example, so in this example, a student carried out a back titration to determine the mass in grams of calcium carbonate present in a 0.125 gram sample of eggshell. The eggshell was reacted with 100 centimeters cubed of 0.1 moles per dm cubed hydrochloric acid, and the excess HCl was then titrated with 0.500 moles dm cubed of sodium hydroxide. The average sodium hydroxide titer was 16.06 centimeters cubed, and we asked to calculate the mass of calcium carbonate in grams present in the eggshell. So the first step is to determine the amount in moles of 0.500 mole per dm cubed sodium hydroxide that reacted with the excess. So we know that the average titer was 16.06. So this means that given moles equals concentrations times volume, we have the concentration of 0.5 times the average titer of 16.06. However, this needs to be converted to decimeters cubed, so we're going to times that by 10 to the power of negative 3, which gives us moles of 8.03 times 10 to the power of negative 3 moles of sodium hydroxide that reacted with the excess HCl. The next step then is to determine the excess HCl present, which, as there is a 1-to-1 ratio, this means that there was 8.03 times 10 to the power of negative 3 moles in excess. So then we have to determine the amount of 0.1 moles per dm cubed HCl that reacted with the eggshell. So the initial amount of HCl is given by 0.1 times 100 divided by 1,000, which gives us 0.01 moles. Then we subtract this, the excess moles from this, which gives us 1.97 times 10 to the power of negative 3. In step 4, we need to determine the amount of calcium carbonate that is reacted with the HCl. So in the equation there is a ratio of 1 to 2 of calcium carbonate to HCl. Therefore, we have half the amount of calcium carbonate as we do HCl. So therefore we have 9.85 times 10 to the power of negative 4 moles of calcium carbonate. We can then use this moles in a calculation to find the mass in grams using the molar mass.